Section 9.4 is about rotation and systems of quadratic equations. For those of you who are gamers who have played flight simulator games, this is the mathematics that allows the screen to roll like this when you're playing that kind of a game. As an example, I have 3 points in the plane. And the coordinates of these points in the xy plane is 1 square root of 3, square root of 2, square root of 2, and square root of 3, 1. Now, we spent quite a bit of time learning coordinates like these with the unit circle in trigonometry. And we know that the distance from the center to each one of these points is actually equal to 2. Assuming you do recall that, I'm going to introduce a new coordinate system, the x primed, y primed coordinate system. And I'm just going to lay it over the top of the other one. Now, if the angle theta was 0, then these two coordinate systems would be the same, the x primed, y primed, and the xy. But if I turn this, and I call this angle right here between the x primed and the x, if that's my theta, then if I turn this right here to a 30-degree angle, then when this is 30 degrees, my coordinate for P1 would be 2, 0 in the x primed, y primed. So I could write this as 2, 0, and if I keep rotating this to 45 degrees, then it's P2 that would be 2, 0 in the x primed, y primed. So this one would be 2, 0. And if I rotate even farther to an angle of 60 degrees, so here's my 60 degrees, then it's 2, 0 in the x primed, y primed coordinate system for P3. What's my point, you might ask? Well, my point is this: the representation of a point in the x primed, y primed coordinate system depends on the angle that the coordinate system is rotated. So if I rotate 30 degrees, I can get a point to look different. 45 degrees, I can make another point look different, and so on. The example before this might make it easier to accept what I'm going to show you now. Look at this ellipse. It doesn't look like what we've done before. Our ellipses have always been horizontal or vertical, but this one is tilted at an angle. What that does to the ellipse equation is it changes the way that it appears. This one is 7x squared minus 6 root 3 xy plus 13 y squared minus 16 equals 0. Now, that doesn't look like anything that we've done yet, especially this term here that has x times y. And you cannot complete the square when you have a term like this in your equation. Let me show you how we can use rotation of coordinates to make this problem a little bit easier to work with. I'm going to introduce the x primed, y primed again. And if I rotate the x primed, y primed coordinate system like this, I can get it to line up with the major and minor axes of the ellipse. And this would be 1 and this would be 2. Now you could see that the major axis has an A of 2 and a B of 1. And this is actually a pretty simple ellipse. The equation of this ellipse would look like this. In the x-primed, y-primed coordinate system, it's going to look like x primed squared over 2 squared plus y primed squared over 1 squared equals 1. Now comes the hard part. If we were given this equation, and even if we were given this picture, how would we really know that this angle had to be 30 degrees? And how would we get from here to here? I mean, we could lay this on the picture like this, but we couldn't really be sure that this was 29 or 30 or 31. So we have to have some way of finding this angle theta. And even after we find this angle theta, we have to have some way of making this equation change into this equation. And that's the subject of the next video.